For our system design project, Victoria, Matt, and I chose the problem space of food fraud. We know that artificial intelligence is opening up so many amazing possibilities in so many fields, and since food fraud detection already depends heavily on technology and computing, we thought that integrating AI would be a natural fit. So, looking into the possibilities, we discovered that AI can be applied to two critical functions of food fraud detection: real time monitoring and enhanced analytical insights. Speed, accuracy, and throughput can be greatly enhanced using Internet of Things enabled sampling machines and AI powered edge computing. Also, by integrating external data sets with internal sampling data using machine learning models, powerful insights can be gained for interested parties such as regulatory bodies, NGOs, and food chain suppliers. All of this can be built into a scalable system ready for more types of sampling methods and more types of internal and external data sets. A search of existing systems revealed that AI integration into food fraud detection systems is in its infancy, which is not surprising considering that around the year 2020 is when the AI boom really took off with accessible tools and deep learning ability. Here on this slide, we see that a few food fraud detection companies are integrating AI algorithms into their spectral imaging and other monitoring methods. So spectral imaging is one of the easiest methods for application of AI because it provides high dimensional data. It is non-destructive and rapid, which lends to real-time processing. It has substantial research backing, and spectral imaging is highly compatible with classification algorithms. And other companies are focusing on integrating vast numbers of data sets from diverse sources and applying AI to provide risk management services, business intelligence, and context-specific insights. All the while, research on many fronts is being carried out as AI and machine learning technology continues to advance. So, considering the vital nature of food supply systems to human health and economies, and the constant threat of food fraud, which leads to economic damage and human health hazards, the application of AI to food fraud detection represents fertile ground for business opportunity. For requirements gathering, we interviewed several stakeholders, including the business CTO, top management, data analyst, sales team members, and customers. We supplemented this with document analysis. We identified the functional and non-functional requirements summarized here on this slide. So the general consensus on functional requirements includes integrating AI modules into spectral sampling platforms to enable real-time monitoring, creating a secure framework for transmitting real-time data and ingesting external data sets, as well as integrating AI modules into the analytical platform. Training employees and ensuring seamless integration and comprehensive data QA/QC also ranked as top priority. Just as important is the need to build an effective web-based portal for customers to access their real-time monitoring dashboard and the analytical reports. These are the two avenues that we're pursuing, of course. This dashboard will also enable data analysts and sales team members to perform their duties as far as generating reports, placing reports on the platform, and then the sales team members making those available to customers. So we constructed a number of data flow diagrams, logical data flow diagrams, beginning, of course, with the context data flow diagram, which is presented here. And this shows a top level view from sampled food sources through the food fraud detection system, finally reaching customers with an array of end products while allowing for customer feedback. The following logical data flow diagrams visualize processes of the system. Our level 0 enhanced data reporting DFD captures the processes involved in integrating and analyzing internal and external data, performing QA/QC, generating reports, and the customer accessing the final products of AI-powered analytical insights, as well as educational and demonstration material. Our level 0 real-time monitoring DFD captures the processes involved in remote monitoring and data transmission, data QA/QC, and customer access to real-time monitoring. And next we'll look at our level 1 DFDs. So this level 1 DFD, the enhanced analytical reports, this decomposes that level 0 process to show further details of spectral data processing, integration with external data and analytics by ML machine learning models, approval and feedback for ML models, and AI reports generated and stored for the sales team. The level 1 data QA/QC DFD decomposes that level 0 process to show data reception and notification, automated data checks, manual review of anomalies, and any needed data corrections. The level 1 DFD titled Customer Access to AI module decomposes that level 0 process to show access to the customer portal, report and demonstration products, AI-powered packages, customer account, and data requests. This level 1 DFD called Customer Access to Education and Solution decomposes that level 0 process to show updating educational content, customer portal navigation, and finalizing sales arrangements. This level 1 DFD, remote monitoring and data transmission, decomposes that level 0 process to show edge AI activities, manual review and approval, and data transmittal to central database. And the final level 1 DFD, called Customer Access to Real-Time Monitoring, decomposes that level 0 process to show the customer portal, demonstration products, customer account, and customer requests. And here we start with our physical data flow diagrams, and of course these provide additional details that include process notations for programs and procedures, names of database stores, files involved in data flows, and human-computer boundaries. And I'll just go through these kind of slowly. Here's our level 0 real-time monitoring, level 1 enhanced analytical reports, level 1 perform data QA/QC, level 1 customer access to AI module, level 1 customer accesses education and solutions, level 1 remote monitoring and data transmission, and level 1 customer access to real-time monitoring. So this slide presents our computing architecture, and we chose a client-serving computer architecture. This makes the most sense for this system due to scalability and ability to accommodate multiple users, middleware functionality, separation of basic functions, and resilience. Of course, the client-server approach is widely used for many enterprise systems today because it offers centralized management and enhanced security, and generally allows for better performance.
Okay, now I'm going to give a rundown of our database design. I'll show how each step in our food fraud workflow maps into tables and relationships you can see in this physical ERD. So on the far left here, we have the spectral machine table. Here is where we register each IoT spectrometer by its unique machine ID, lab location, make and model, and the last calibration date. When a device scans a sample, it writes a record into the spectral data table over here, linking back via the machine's ID, so we always know which device that came from. Before, however, it goes to the spectral data table, the spectrometer flow goes into the edge server. This represents the on-site compute node that first receives spectral data for immediate AI analysis. So every time a machine scans a sample, the raw data readings flow into our edge server, which sits right alongside the spectrometer. Think of the edge server as a local hub. So it batches up readings, applies quick sanity checks, like did the device drift, and then it encrypts everything before forwarding to the central system. We record the server's network details, rack location, and timestamp of the last data batch it processed. So if our central server ever goes offline, no data is lost at the edge. Next comes our ingested data table, which ties together both spectrometer readings and any external data set imports. So each row records the ingestion timestamp, data format, and then source reference, and links back to both the spectral ID and the external dataset ID fields. So we maintain clear provenance whether the data came from our machines or regulatory FTP feed. After ingestion, data moves into the verified data table, where automated and manual QA checks mark each record as a pass or fail and record the verified value and status. We link back to this original ingestion row so we can always audit what was approved. Every manual review step is carefully captured in the QA/QC log, which records who checked the data, when, and with what outcome as well. If a reading needs correction, we create a record in the correction request table, tracking the request fix, its status, resolution date, and the analyst responsible. Once data is verified, it feeds into the report data table. This links each approved data point to a specific dashboard report via foreign keys to verified data ID and dashboard report ID. That way, when you see an anomaly in the dashboard, you can easily drill backwards to see exactly which measurement caused it. The dashboard report table itself stores metadata for every report, its type, name, creation date, and data source. So any report can be rerun or audited on demand. Finally, on the far right, we manage user resources and feedback. The category table organizes our in-app tutorials and user guides, while the customer and sales team tables capture who's selling the system and using it. We tie any feedback into customer feedback and report feedback, linking back both to the report and to the account that submitted it. This closes the loop for continuous improvement and ensures every comment is traceable right to the source. So why did we choose this structure here? Basically, we chose 5 key points. The first being traceability. So every piece of data from raw spectrum to polished report carries lineage through the foreign keys. We also wanted to ensure integrity. So we enforce referential links so you can't verify or report on data that wasn't properly ingested. Third is resilience. The edge server layer lets us process and buffer data locally if there's ever a network hiccup. Fourth is modularity. Splitting ingestion, QA reporting, and feedback into separate tables mirrors our 4 core system modules, making both development and future changes pretty straightforward. The fifth and final reason is performance, right? Narrow, well-indexed tables and sharding at the edge let us handle high volume streams without sacrificing real-time query speed. Basically, our design underpins our promise of transparent, auditable pipeline from the moment a spectrometer beam hits your sample to the instant an alert appears on your dashboard. Okay, here's a quick tour of our 3 sets of hand-drawn screens for the user guide documentation. Up first are the customer screens. On the left here, we have the login screen, which features a center logo, the food adulteration system login banner, and then a simple username and password entry form. On the dashboard screen, we have the title bar that reads Food Adulteration Monitoring and Analytics Dashboard. On the left rail, you have sensor feed and analytics, and on the right, you have education and demo. Across the bottom, we keep a theme with current alerts and download. The large sensor panel is, of course, reserved for the live sensor feed, which is most important on all of these models. Next is the analyst dashboard. Very similar design, same basic layout as a customer, username, password. On the dashboard, well, the left rail actions are review real-time data and review spectral data sets. Right rail actions include upload external data sets, ingest data, access MLL pipeline, and generate reports. Bottom buttons remain the same, current alerts and download, and so does the center, which shows the live sensor feed on the main dashboard. Next, we have the sales team dashboard. Again, same basic layout as the branded login form. And in the dashboard view on the left, you will see demo portal, customer portal, and on the right, educational content and enhanced analytics. The center panel is relabeled demo live sensor feed as no live data is shown to for educational purposes. The bottom row again is customer alerts and download. So each one of these sketches maps directly to our interface standard metaphors. The control panel flows to the central canvas, inbox, alerts list, etc., and shows how we tailor the same core dashboard to each user role. And now we have the Windows navigation diagram for our system. Here is our main dashboard template. Right here, we have the logo button that returns every user back to the main dashboard. On this main rail, you'll see we have enhanced analytics, which is our AI-powered workbench for deeper insights. The center area basically displays contextual widgets, live alerts, model explanations, and drill down charts. So we've kept the layout really clean so a data analyst can jump on in from the live feed to an insight report in just one single click. All core actions like generate reports, ingest data, access ML pipeline, upload external data sets, and review alerts, they live in this unified menu bar here, and we can move on to their actions by a single click. Our in-app documentation plan is pretty cool. So when any user needs help, they would click the help icon right here, which is located in the top right. So that launches our Alevio widget, which is right inside the dashboard. There's no extra windows, no separate login required. It's right behind the scenes. Alevio's AI assistant, which is Java-based, surfaces the exact guide, tutorial, or video they will need, whether it's performing QA/QC checks, uploading external data, generating an insight report, any of this. It's all right there with a single click and ran by an AI assistant. If the built-in articles or videos don't fully answer the user's questions, they can open a ticket that flows straight into our Jira, and it's all tied back to this screen where they can click help. Up next are our lessons learned. We all put in our input here, and I'm just going to go ahead and summarize them. So by rigorously following each SDLC phase, thorough planning, in-depth requirements analysis, detailed design, and modular development, we avoided costly missteps. We kept stakeholders aligned, and we also ensured that each component was thoughtfully and thoroughly specified and easily tested. For the future plans for the system, we also all put our input here, but I'll summarize again. And basically, what we plan to do is package this solution as a turnkey, edge-in-the-box, smaller implementation for local deployment. We want to expand AI/ML to additional detection methods and traceability technologies. Think things like chromatography or even blockchain. And we want to evolve this toward proactive global food safety monitoring via satellites and mobile integration. So our AI-powered food fraud detection system will deliver end-to-end transparency, rapid alerts, and scalable analytics. This will set a new standard for safeguarding the food supply.